Good morning. Hope you are all fine. Today we are not introducing any new theory topic. Instead of it, we will try to do some of the problems from the topics which we have already discussed. In here, in two lectures, I will discuss only 7 problems, but you can see a large number of problems in any electronic textbooks. So try to do as much as problems you can, because trying to do problems and doing problems more and more will make you the theories more clear. So to get in familiar with the theories we are discussed, you need to do much number of problems or more number of problems, and by doing the problems only we can be familiar with the theories. The circuit analysis techniques and solving the different electronic circuits will make you clear only when you are doing the problems. So that's why I'm introduced special sessions for doing the problems. In the first few lectures we are having the problems, and after that we are giving you some quiz questions in the form of problems to test whether you are understood the theories or not. Here I am discussing these 7 different problems which will try to introduce you or make you familiar with the theories which we have already discussed. And remember that these 7 problems are not enough to make you familiar with your theories. So remember that this is only the beginning. From here onwards you start doing problems, and if you are having any doubts or if you get stuck with any problems while doing, you can contact me to discuss your doubts and all. So this my humble request to you is that try to do more number of problems to make you clear the theories as well as to make you more interesting in the subject. Okay, let's see first problem. Here the question is, what is the current in the circuit shown in figure? Assume the forward resistance of the diode to be 2 ohms. So here we are given with a very simple circuit which contains a voltage source of voltage 5 volt, which is connected in series with a diode D, and which is represented by Si, which is represents the silicon diode. So a voltage source of 5 volt is connected in series with a silicon diode and is then connected to a load resistance of 10 ohms. Just denoted 10, so it represents 10 ohms. And we are given with the forward resistance of the silicon diode is 2 ohms. So you cannot rate the silicon diode to be an ideal one. The forward resistance is given, that is, we can list out the given things. The voltage V in is, I am representing it by Vi, which is equal to 5 volt. The load resistance RL is 10 ohm, and the forward resistance of the diode, we are while discussing the theory we used it to represent the forward resistance by RF, which is equal to 2 ohms. And one more information we can draw from this circuit is that this diode is made up of silicon. Silicon means then we can have the V knee voltage, the voltage which needed to overcome the potential barrier is V0, or VNE. It is better to use VNE because V0 we are used to for the output voltage, for representing the output voltage. So VNE voltage is 0.7 volt. If it is a germanium, then this new voltage is 0.3 volt. Remember these two quantities or parameters. For silicon diode, the new voltage is 0.7 always, and for germanium it is 0.3 volt. These two things will be in our mind. So now these are the given quantities. We want to calculate the current. So I am going to replace this circuit by its equivalent circuit in order to solve the circuit or to analyze the circuit, because in the theory sessions I told you that to solve a circuit it is better to replace it by its equivalent circuit. Here we are having a circuit element diode, so we have to replace this diode by its equivalent circuit, then it is easy to analyze the circuit. So first of all I am drawing the DC voltage source here as 5 volt. Then the silicon diode. So a diode can be replaced by a voltage source equal to its new voltage and or the potential barrier and the forward resistance. So here we can have positive here, negative here with a small resistance RF here, and the load resistance RL is here. So this is the equivalent circuit, and the quantities are 5 volt here, this is 0.7 volt, and this is 2 ohm is given, and this is 10 ohm. So now if you consider to solve this is a simple circuit, we can use the Kirchhoff's voltage law. When we are applying the Kirchhoff's voltage law, let's start with from this position A, B, C, D and A. Let's go like this. From when we are going from A to B, we are having the voltage source. It is from negative. In the electrical technology we have studied how to solve a circuit, and if we are going in the direction from the negative polarity to the positive polarity, there is a rise in potential. It is represented by the positive sign. If we are going from positive to negative, there is a lower in potential which is represented by negative sign. So here when you are going from A to B, we are having going from the negative terminal of the battery to the positive terminal, so we are having a rise in potential, so it is represented by 5 volt. Now from B to C there is two voltages. One is the voltage which is represented by 0.7 volt, the knee voltage, and there is a small resistance R of the forward resistance, so there is a potential drop across this resistance that I can represent it by, if I is the current through the circuit, then it is 2 into I will be the potential drop. So it is for when we are going from B to C, first we have to encounter this 0.7 volt, where for 0.7 we are going from the positive terminal to negative terminal, so from higher potential to lower potential we are going. That means we are suffering a lowering potential, so lowering potential is represented by minus sign, so minus 0.7. then we are assumed that the current is flowing from B to C, so current will always flow from a higher potential to lower potential, so we are moving in the direction of the current. If we are moving in the direction of the current, it is represented by minus sign, so here it is minus I into R is 2 ohm. Then from C to D, again the current will flow in the same direction, that is from C to D, and we are moving in the same direction, so it is again represented by lowering potential. The current through the load resistance is again I, because it is connected in series. So I into 10 is equal to 0 according to Kirchhoff's voltage law. That means we are applying the KVL here, Kirchhoff's voltage law, to this circuit. Now if we solve this one, we can see that 5 minus 0.7 is 4.3 minus I into, if you take I outside, minus I outside, it is 2 plus 10, that is 12, is equal to 0. Then I will be equal to 12 by 4.3, sorry, I will be equal to 4.3 divided by 12, which you can obtain as a numerical value, represent it in milliampere. I am not giving the final answer here because you have to calculate this value 4.3 by 12 and replay the answer to this question as you are ensuring, in order to ensure your participation of the lecture. So again I'm telling you that reply to this lecture, I will upload it in the Google Classroom. So you have to go to the Google Classroom and comment the numerical value of this answer. As for question number 1, write your answer as the comment to this lecture in order to ensure your participation in the lecture and your involvement in the lecture. So you are having a assignment to ensure your participation, and you have to comment the answer to this question as your attendance mark, for your attendance marking. Okay, now let's see the second question. That is another question, another very simple question. Determine the output waveform for the network and calculate the DC level and the required peak inverse voltage of each diode. Again question, determine the output waveform of the network and calculate the output DC and the required peak inverse voltage. Output voltage here given across this 2 kilo ohm resistor and is represented by V0. So we have to calculate the voltage across this 2 kilo ohm resistance, and 2 diodes are connected here. Since nothing is specified in regard to the diodes, we can take this diode to be ideal. Means the internal resistance of the diode can be taken to be 0, and the knee voltage also we can take it to be 0. So since it is not specified, we can take the diodes to be ideal one. So it becomes more simple. So now what we are going to find out is not the voltage across V0. We definitely to draw the not only to find V0, we have to draw the DC output level. What should be the output waveform we have to represent. So let's start this one by replacing the circuit by its equivalent circuit. Remember that the input is an AC signal with 10 volt as the maximum voltage. That means we can write the given voltage for V in, the maximum Vm is given by 10 volt. So now since the AC is given to a circuit containing diode, while discussing the equivalent circuit or while replacing the circuit by its equivalent circuit, we should have two parts. We will consider how the circuit behaves during the positive half cycle, then we have to consider how the circuit behaves during the negative half cycle. So we have to consider the two half cycles separately. The behavior of the circuit we have to consider for the positive half cycle first, then we have to consider the behavior of the circuit or the equivalent circuit for the negative half cycle. So first of all, I am denoting this diode as D1 and this diode as D2 because it is not given here. For the sake of our convenience, I am just denoting the diodes D1 and D2. And the resistances where this one is representing by the resistor across which the output is to be taken is represented by RL, and the resistance I am representing it as R1 and this as R2, and I am going to name these nodes as A, B and C. A, this is node A, this is node B, and this is node C, and this is node D. So across the branch AD, the diode D2 is connected. Across the branch AC, diode D1 is connected. Across the branch BC, resistance R1 is connected. Across the branch BD, the resistance R2 is connected. And across the CD, the branch CD, we are taking the output, the load resistance is connected across that branch. And so now, using these notations, we are going to consider the equivalent circuit of this one for positive half cycle and for negative half cycle. So here during the positive half cycle, let's see, this end A is positive and this end B is negative, let's say. Then A is positive means D1 is forward bias during positive half cycle. D1 is forward biased and D2 is reverse biased. That means D1 can be replaced by a short circuit and D2 can be replaced by an open circuit. So the equivalent circuit I am drawing to the next page. So we are having the node A here, then D1 is replaced by a short circuit, D2 is replaced by an open circuit. This is C, this is D. Across CD we are having the load resistance. Now we are having a resistance here across BC, and across BD we are having another resistance. So this is B, this is so this is the node B, and this will be the equivalent circuit, and current will flow in this direction. I am representing it by the red line, red arrow. Some current will flow here and current will flow through here. That is, current from AC is divided into two parts, one towards D and one towards B. and this is the red arrows represents the direction of the current. Now I am going to replace this one again. If you consider, we are having SC, this is A, this is C, no resistance. Suppose this is D, then we are having D here, now D is here, so this is B. This one is the node B, this is the node C, and this is node D. Here it is 2, here it is 2, here it is 2. And remember that we want to find the voltage across CD, that is, we want to find the voltage across V0. So now the maximum voltage which will appear across this node AB is the maximum voltage of the input signal, that is VM, that is VAB. VAB is equal to VM, which is equal to 10 volt. Then which will be, since B and C are parallel, the voltage across CD, that is CDB, will be same as the voltage across CB because they are parallel. Now if we consider these two, the voltage across CD will be equal to voltage across DB, because current will be the same and the resistances are the same across CD and across BD. So VCD is equal to VDB, which is equal to the half of the total voltage VAB, or here we can write it as VCB by 2. A and C are at the same potential, so A and C are the same, so that's why across A and B, across C and B, the potential difference will be the same. Half of it will appear across the CD and half of it will appear across BD, so it will be VAB is VM, that is 10 volt by 2, so we will have 5 volt output. And the direction of the current here I am going to represent by the red line. Look into here, here it is positive and here it is negative, so current at this node C will be divided and will flow from C to D. So the current direction is C to D during the positive half cycle with a voltage of 5 volts. So if input is 10 volt, then we can have during positive half cycle a output like this, and the VM is given by here 5 volt, that is voltage across CD is 5, so the maximum voltage will be VM, which is equal to 5 volt, and the direction of the current is from C to D. Keep this in mind. And now we are going to analyze the circuit by negative half cycle. So when it is during the negative half cycle, this end is negative, A is negative, B is positive, So when we consider this condition during negative half cycle, D1 A is negative, so D1 is reverse biased and D2 is forward biased. So if D1 is reverse biased, it can be replaced by an open circuit, and D2 is forward biased, it can be replaced by a short circuit. So let's draw the equivalent circuit here. Here we are having the A. At A, the diode D1 position is open and D2 is short. This is C and this is the node D, across which we are having the load resistance, and the node B is here. From B to C we are having another resistance 2 kilo ohm, and from B to D we are having another resistance 2 kilo ohm, and this is A, this is B. Here it is positive and here it is negative. Now we can replace it by redraw like this. At end A, suppose this is A, then it is D is also having the same potential because they are connected by just a zero resistance wire ideally, and we are having B, a resistance of 2 kilo ohm is connected across it, and this is the node B. So this part we have drawn like this, BD. Now if we consider the node D, D to C we are having like this, D to C, then C to B, and we are having like this. So this is the equivalent circuit. This is the our load resistance CD. We have to consider this voltage VL across this 2 kilo ohm resistance. Again across BD we are having positive and negative, so I am going to represent the direction of the current by the red lines. So from B, current will reach the node B. At B it will divide into towards the node D and towards the node C, and the current will flow here, and from here. So the red arrows represents the direction of the current through this circuit during the negative half cycle. Now we have to calculate what is V0 across BA, that is the input voltage appears across BA, which is VBA, will be 10 volt because it is the maximum voltage of the input signal, and it will be divided to the node towards D through 2 kilo ohm and towards D through C. So since these two are parallel, the voltage across this branch and this branch, that is this branch and this branch are parallel, the voltage across these two branches are the same. So that voltage will be Vm. So which will be equal to VBD. Now if you consider this branch BCD, the branch BCD, I'm just drawing like this here. Here it is B, it is D, here it is C. Here the resistance is 2, here the resistance is 2. Since the resistance are same, the voltage across BD will drop across these two resistances equally. Since they are in series and the resistances are same, the voltage across each branch, that is BC, will be equal to VBC will be equal to VCD, and this will be the half of the voltage across BD, VBD by 2, which will be again 10 by 2 is 5 volt. So the voltage across this is 5 volt. Now the voltage across CD, that is the required value, the voltage across CD, that is the load resistance across CD, we are connecting the load resistance, which is again 5 volt. Now if we consider the direction of the current, you can see that the current flows from here to here, that is represented by this red line. So it again flows from, current flows from C to D. So in the previous case also current flows from C to D, and here also current flows from C to D. So if you draw this one for the negative half cycle, for the positive half cycle we will have a voltage like this, for the negative half cycle also we will have a voltage like this. Both the voltages will have a peak value Vm.